Hang on. Hello. At 8 o'clock, we'll be bringing you December's Tonight at 8 webinar, Dipole Basics with Steve Stearns, K6OIK. But first, we're going to look back at an interview from last year's RSGB convention, where RSGB Comms Manager Heather Parsons, M7OWS, talked to RSGB General Manager Steve Thomas, M1ACB, about the project he led to develop the new RSGB app for mobile devices.
Hello, I'm Heather, the RSGB Communications Manager. I'm here with Steve, the RSGB General Manager, and we're going to be having a chat about the RSGB digital platform. Now, we know that many of you have already downloaded the RSGB mobile app that we launched this week, and you're already enjoying the benefits of that. But today we wanted to give you a little bit of a glimpse behind the scenes as to what's been happening to get to this point for the launch. So Steve, before we get to what's been happening, let's start with the why. Why did the RSGB decide to launch a digital platform?
Yeah, why? Really good question. Sometimes I ask that of myself through the project. You know, you always do. But it was absolutely the right thing to do, because we had members asking us for a digital platform, and we also wanted ways of bringing the other parts of our communications, digital communications, into our main members' benefit, which is RADCOM, bringing it all together. So it was really because people were asking, and we knew it was a good thing to do, but it was quite the journey, as you know. Absolutely.
So why did we start with the web app first? Let's explain what led up to that and why we chose to do that.
We have to go back even further than that, actually, because once we look for modern tools to present RADCOM and the whole RADCOM family, we realised that our membership system needed to be updated to work with those modern applications. Yeah. So we had to go right back to that and change our membership system to a much more modern system that would work with the APIs into the publishing tools. So we had to go right there. Now that's quite a major change for a membership organisation to change their membership tools. Yeah. So we started that journey probably a couple of years ago, I think, really. But that's had lots of benefits as well in the way we communicate with our members. But for this purposes of the app launch and everything like that, it was absolutely key. We started then with the web app, as we called it. It's something called a progressive web app, which means it's just a fancy word really. It adapts to the type of screen you're using it on. So you can use it on PC or mobile or tablet, but it's still a web app, a web version. So we started there, and we wanted to get members used to using their credentials that they use for the membership portal on a website, also into the publishing tool, let's call it the web app version, and we wanted to improve the I've forgotten my password process and everything like that to make it much more automatic. We just needed to get people to get used to that, while we spent the time looking at our back editions, because we've loaded 25 years, isn't it, back to the year 2000. So we've loaded 25 years, that's 300 editions of RADCOM. And I feel like I know each of them individually now, those 300 editions. But we had to go back and rework some of those, because PDF technology has moved on and desktop publishing tools have moved on in those 25 years. So we went back and we improved quite a few of those editions, up the resolution, things like that. So we were doing all of that while the membership were using the web app, which we launched last May. So it wasn't just there was a big delay, we were doing a lot of work behind the scenes. So that's what we wanted to do first, before we got to actually launching the web app. Gave us an opportunity as well to look at the functionality within the web app that we wanted to pull over into the mobile app.
There's some fantastic things within it, aren't there?
Yeah. It was a classic sort of agile project, in that you deliver as much as you can and then you improve and you build on it, and it culminated in the launch of the mobile app last week.
Indeed. So, and in both the web app and the mobile app, we've been able to blend together more of our content in different ways. So, for example, if there's a review in RADCOM of a piece of amateur radio equipment, then we've been able to do a video review as we did in the September issue.
Yeah. And we did, and I've used that a number of times in demonstrations at the National Hamfest and here at the convention. We recorded some how-to videos yesterday, didn't we?
Yeah, we did.
You know, it's been a big thing for us. And using that example where somebody writes a review for us and records a YouTube video, and we've got an advert it was for an antenna, wasn't it, that we were using in an example. And you can look at all of that, read the review, click on the video, watch the video, click on the address to actually buy it, and take you through to the shop, all within the web app. And that's what we wanted to do, was bring all of our communications channels, which you know a thing or two about, let's be honest, together with one of our biggest members' benefits, which is of course RADCOM and everything like that. And then we wanted to give people access to the archive. We wanted to bring in RADCOM Basics, RADCOM Plus, because a lot of people, they all know about RADCOM, and they don't all know about RADCOM Plus and RADCOM Basics for the try something new and the more advanced editions that we do. But putting that all together in the same app means that people are going to see it.
Indeed, yes, because you can already sign up to be notified when the latest RADCOM Basics or RADCOM Plus arrives. Not everybody does that, and as you say, not everybody then finds the content. So having that in that one-stop shop, almost as we could call it, in that one place, is a brilliant resource for members.
And the other thing that we've got the opportunity to do, and we've done, is we can have a sample area within the web app as well, the web app and the mobile app, across the whole piece. And we can put in there, we've got in there actually a sample edition of RADCOM. So if we want to publish something so people can get a flavour of RADCOM, see what they're missing, really, in membership terms. But we can put something there that's really important as well. And the one we've got there at the moment goes back to the Ofcom licensing review last year that we wanted to make public for absolutely everybody so they could see about the consultation. So that one's in there. And we've also got 3 really historic editions in there.
TR Bulletin.
Yes, absolutely. So from 100 years, from 75 and 50 years. And those have been really fascinating for people to look at. When I was over in Dayton, the American visitors to Dayton were absolutely fascinated to look at the old historic versions, the very first edition of the TNR Bulletin, for instance. We also use this for the club's newsletter as well, which we make open access, because we can't assume that everybody who's a member of a local club is actually a member of the RSGB. So, but this means that we can share the club's newsletter with the club secretary, and they can pass that on to all of their members by looking at it through the app. But again, that just brings awareness of the products that we've got in there. So brings it all together. Now, but I know, especially over the last few days, that we've had some fantastic feedback, because we're talking now only, what is it, 4 days after
4 days
launched?
since we launched the mobile app, yes.
But we've had some amazing feedback, haven't we?
have.
You've been on the receiving end of a lot of that. Comms manager, you're going to see
it. We've seen.
What we heard. Let me interview you for a second. What have we heard?
We've seen some brilliant things, and I think on the screen you're going to be seeing some of those comments now. We've been seeing people say it's the best thing since sliced bread, really easy to navigate. Brilliant app. They're delighted to be able to now get rid of their paper RADCOMs, save themselves some space, and people have also been talking about the environmental aspect as well of going digital and saving paper, saving trees, whatever. If that's important to you, then that's something that the mobile app certainly gives you. And we've had comments not only from people nationally but internationally as well, who people are downloading now.
I was going to say, it surprised me when I looked, because I've been looking at the Google and the Apple statistics behind the scenes, and it surprised me that it said we were launched in 175 countries. And
that's quite mind-blowing, isn't it?
That got my attention. So this is a worldwide opportunity for people to see. But of course, using those 2 very popular platforms, plus the web version that we've got. So, and the web, if you've got a browser, then you could use it. So if you're a Windows or a Mac or a Linux user or anything else, if you've got a browser, then you can use the web version. And the mobile edition we do for Android and Apple. And the extra benefit you get with that is that you can actually download for offline viewing.
Yeah.
It's still within the app,
Yeah.
right? But you can actually download. So if you're going on a plane or something like that,
Yeah.
you can still
Going
read
somewhere with that
offline. Or
signal.
you're out of Wi-Fi
Okay,
signal.
yeah, you can still
then
do.
that's the additional thing that comes with the mobile app.
Yeah, absolutely.
But the feedback here has been amazing, isn't it? And we did a show of hands at the opening ceremony of how many people have, launched the app, and hands went up.
Yeah, I was talking to
hit me there.
I'm sure it did. It's been a major project for you. It's been your project, really.
Yeah.
And you've been supported hugely by Anna, our marketing strategy manager, who's done a fantastic amount of work on that as well.
And the important thing there is,
it's a team.
I come from an IT background. Before I've been doing this, I keep saying that, but I've been doing this job nearly 10 years now at the RSGB. But come from an IT background, and I wanted other people that were going to be users or see it from the user's point of view, and Anna's been great at that, and working with me and the developers to try and make it easy to use and understandable, and it's been a great part of the.
Her eye for detail is very good.
Oh, yeah,
very helpful.
Yeah.
So going back to the mobile app which we've launched today, and we've spoken a little bit about some of the ways that we've been able to blend our content. And people will see that every time there's a URL that comes up, we're pointing people either to our website or to other places. That is automatically a clickable link, and it will take you directly to that place, obviously within the app. And so, for example, for us as the RSGB, we want to make sure that everybody's aware of all the fabulous resources and RSGB benefits that we provide.
Yeah.
And we're aware that not all of our communications channels hit people. People look in different ways. But now, if you're reading RADCOM on the web app or on the mobile app, we're talking about the latest Tonight at 8, for example, that's coming up, our online webinar that we do each month, and we have a global audience for that. But if you click on the logo or click on the link, that will take you onto our website, and you'll be able to see the whole list of the programme that's coming up over the next few months. And also that it has huge potential for advertisers and things as well, doesn't it?
Yeah, it does. Just easy answer, if advertisers include a URL in their advert, then it becomes clickable in the app.
Yeah.
And I've spent some time talking to those advertisers and the manufacturers and the dealers, those who advertise with us, very excited to follow that through. But we've been looking at all of our publication process, because we need to start some of those things, really right at the design stage when we're putting RADCOM together.
Yeah.
But then we link together our YouTube channel, our social media activities. And we can even share a link that's a deep link right into an article. If you're an RSGB member and you see a link, it can be to an article. As long as you can log into the app, it'll take you right to the page. So we can do things both ways. It's really powerful. And the company we've been working with, they've got some really big organisations that are using their app as well as us.
Yeah.
So we're benefiting. But they've seen with us that our membership use things in a different way.
Yeah.
So it's not just us being a small player. Yeah. They've seen a different market from us as well. So it's been really interesting.
Yeah. And obviously this is a membership benefit, available for use by members to see RADCOM Basics, RADCOM Plus. And how do you see that? How do you see that happening? What do you see happening next? How do you think people are going to use it? I mean, we've seen the fantastic response we've had now.
Yeah.
I was talking to people in the bar last night about why people should be an RSGB member, and it was great to see some of them saying, I was probably one of the first to download the app. It's just brilliant. Yeah. And we're seeing that spread, aren't we? So
we are. Different people want to use it in different ways.
Exactly.
Like there are some people, and we absolutely understand this, that say don't get rid of paper whatever you do, because I love the tangible feel of the paper. Then there's other people that have been saying for a while, why on earth haven't you got a digital app? Right, we had to bring those two things together and finding something, a publishing route that would give us both. And some people are going to stop taking paper. Yeah. Right, and they just need digital. Some people probably will never look at digital, they'll just carry on with paper. And then there's people in between that are a blend, that they want both, understand that, or maybe they want paper but they're only going to keep 2 years rather than the big stack in the back bedroom. Perhaps they're going to do that, and they're going to use the archive that we've published for the other ones. And that mix, we're just going to find out how that balances out. But we've had a tremendous number of people have downloaded the app just over the last, 4 days since we, it feels like weeks, 4 days since we launched it. You know, the stats have been going up and up and up, which is amazing to see. Made me smile a lot, as you know.
Absolutely. Well, it's been a huge team effort over a period of time, let's say, to get it to this point. It's brilliant to see it out and launched to 174, would you say?
175.
175 countries, with thousands of people we know already downloading it. So just before we finish, what else? What's the one thing you would say to people now about it?
Download it, try it. Let us know how you're using it, but, because we are taking our paper RADCOM and digitising it, so there are some limitations to that, but I'm really fascinated to know how people are going to interact with it. Okay. We're still going to put content on the website, we're still going to have content in RADCOM and across all our other channels, but if we can bring things together, and that's what I'd love to hear from people, how they like it coming together.
Brilliant. Well, you've heard a little bit about what's been happening behind the scenes to get us to this point. We hope if you haven't already downloaded the mobile app, you will do so. You can get it on either the Google or the Apple Play stores, or if you want to try the web app version first, if you prefer to be on a desktop browser, go to rsgb.org/radcom. That's rsgb.org/radcom. And we hope you've enjoyed this little glimpse about behind the scenes as to how we've got to this point with our mobile app. Thanks very much, Steve, for the chat.
Thank you.
And that interview was recorded at last year's RSGB convention, and you can see these and many others on the RSGB YouTube channel in the About the RSGB playlist using this link, youtube.com/theRSGB. Tonight's live webinar, Dipole Basics, starts shortly. Hello and welcome to Tonight at 8 from the RSGB. I think most people would agree that the most important part of any amateur radio station is the antenna. The dipole is one of the most simple but fundamental ones you can have and forms the basis of many different antennae. Tonight, Steve Stearns, K6OIK, joins us to take a look at the properties and characteristics of the dipole. Welcome to Tonight at 8, Steve. Can you give us a quick overview of what you'll be talking about this evening?
Yes, good evening. I'm going to talk about dipoles and a bit of history about the dipole, all the way from Heinrich Hertz to the present time. We'll talk about the behavior of dipoles, and we'll talk about impedance matching of dipoles. We're going to talk a little bit about the theory, quite a bit about theory. We're not going to talk about construction. There's plenty of articles on construction of antennas in the amateur literature. I'm going to focus mainly on the physics. So I hope that'll be an interesting talk.
Absolutely. All right, well, we're looking forward to it. And before we start, if you're watching this on Monday, the 12th of January, then this is live. And you can ask questions or make comments on either YouTube chat or BATC messaging at any time during the presentation or straight afterwards. Please include your first name and call sign if you have one within every message. And note that you can make this video stream fill your screen on most devices, usually by double clicking on the picture or pressing the full screen button. So now let's go back to Steve to find out more about dipole basics.
Well, thank you for that introduction. It's a pleasure to be here tonight. I'm in California speaking to the RSGB group and anyone else who's tuned in on YouTube. It's indeed a pleasure to be invited to give this talk. I've given this talk before in earlier versions of it, but let me first give a brief abstract. The dipole is a very basic antenna, and you can't really understand more complicated antennas without first understanding the dipole. So that will be our goal tonight. There's a lot of facts, some myths, some misinformation. We're going to go through all of that and sort things out. A little bit about me. I'm a retired electrical engineer. I've worked mainly in the United States defense industry for more than 40 years, and in a number of fields, signal processing, communication theory, and toward the end, electromagnetic theory and antennas, as well as electrical network theory. I've got a whole bunch of licenses, which doesn't matter much, but patents and publications. So I've given a lot of talks at ARRL Pacificon Convention, which is held in San Ramon, California every year. All of the slides, or most of the slides, are archived on the website, which can be downloaded and examined. Of course, if you look at slides, you only get the pictures, the graphics, you don't get the talk. But the slides merely illustrate the talk. Recent work has been in insulated wire modeling. How do you model wire antennas that have insulated wire? I had an article in QEX 2 years ago, actually 1 year ago, a talk on the best shape for wire antennas. It turns out you can get great performance improvements from wire antennas if you don't make them straight, but curve them in a certain curve, and that was covered. And then you can also make antennas out of things that are not made out of metal, like trees. And you can make arrays of trees. If you plant your seeds in the right places, positions, let them grow to the correct heights, you can make very fine antennas using just trees. Or if you have a monopole, say in a park, and you put your monopole in front of a tree in the right position, you can get a nice boost in performance. So trees are not your enemy. Let's go on. Albert Einstein was asked how radio works, and what Albert Einstein replied was, you see, wire telegraph is a kind of very, very long cat. You pull his tail in New York, and his head is meowing in Los Angeles. Do you understand this? And radio operates exactly the same way. You send signals here, they receive them there. The only difference is that there is no cat. And I always thought that was quite an interesting explanation. There is no cat. Until Andrew Lloyd Webber came out with a musical called Cats, and we suddenly realized that there's a senior cat, Old Deuteronomy, who sends jellicle cats up past the Russell Hotel, up to the Heaviside Layer. Now, nobody in literature knew what those words meant, but of course, hams will immediately realize the Heaviside Layer is the ionosphere. The cats are being sent into the ionosphere for a job. They're being appointed by the senior cat, Old Deuteronomy. And the only mystery to me was the Russell Hotel, until I realized that Weber borrowed this terminology from T.S. Eliot, and T.S. Eliot wrote Old Possum's Book of Practical Cats back in the late 1930s. And at that time in Great Britain, the talk of the town, the science news was Whitehead and Russell's work on Principia Mathematica. And Eliot, when he refers to the Russell Hotel, he really means to refer to the Hilbert Hotel from David Hilbert, but substituted Russell's name. It is not the Russell Hotel in London. So this is interesting that cats figure in literature into the operating of the ionosphere, or at least they're in the ionosphere. But that does not explain band openings. And I suddenly realized that physics, if you go into quantum physics, then we have Schrodinger's cat. And Schrodinger's cat, his wave function never collapsed. So the cat is still alive and dead half time. So presumably that explains all the band openings. The band is open half time and closed half time between day and night. So we have those explanations, and cats will figure in other areas of our talk. The first thing I'll say is that laws of physics, the nature of the laws of physics is that physical laws state relationships among physical entities or variables. But the relationships are logical, they're not causal. An example of that is Ohm's law. It is descriptive, it is not causal. Voltage doesn't cause current, current doesn't cause voltage, but they coexist, mutually obeying Ohm's law. The same is true in Maxwell's equations. The equations are descriptive but not causal. The electric and magnetic fields coexist. Waves have an electric part and a magnetic part. They coexist, but neither part causes the other. Now, the reason I point this out is because there's a common misconception that I read a lot, that a time-varying magnetic field causes a time-varying electric field, and vice versa. And this is the explanation for wave travel. But actually, it isn't. What happens is that both fields are created simultaneously and together by accelerating charge at a source, and they travel together, but they don't cause each other. And that is a correction to a lot of things you'll read in ham literature. Here's some basic questions. In acoustics, can a loudspeaker have an isotropic pattern? In electromagnetics, can an antenna have an isotropic pattern? And the answers are, for the first question, yes, and for the second question, no. And the reason is because sound waves are longitudinal, and longitudinal waves permit isotropic patterns. Electromagnetic waves are transverse, or TEM. TEM means transverse electromagnetic. And isotropic patterns are impossible for such waves. And this is a consequence of a theorem in mathematics due to L.E.J. Brouwer in 1912, and it goes by the name the Harry-Ball theorem. And what it means is you can't comb the hairs on a head flat without there being a cowlick or a whorl at some point. And for that reason, isotropic patterns are impossible. Nevertheless, we use isotropic patterns as a theoretical baseline for gain measurement, and I'll maybe mention why that is. Here's some other questions about dipoles. As a dipole gets smaller and smaller and eventually shrinks to zero, what does the dipole's gain go to? Does it go to zero? Does it go to negative infinity in dBi units? Or does it go to some other number? And what does the dipole's capture area go to? The effective area of the dipole. The effective area is important for receiving. Can an infinitesimal dipole receive anything? Does it have zero capture area, or does it have some other capture area? And the answers are quite interesting. As the dipole shrinks to zero, the gain drops down, but never goes below 1.5. So at the limit of a zero infinitesimal dipole, the gain is still positive at 1.5 or 1.76 dBi. And the gain of a half-wave dipole is, you probably know, 2.15 dBi. So we've only lost less than a half of a dB by shrinking our antenna. The dipole's capture area also does not go to zero. Even though the physical area goes to zero, the physical cross-sectional area goes to zero, the capture area goes to a finite lower limit, and given by this equation. I won't explain the equation, but it's interesting that it doesn't go to zero. So the physical capture area and the electrical capture area, the physical area and the electrical capture area are different, and we'll get more into that. And this is, of course, good news for hams who want to operate very low frequency or long wavelength bands, because they can use electrically small antennas and they will still work. What you do lose is bandwidth. The general talk of this antenna is I'm going to focus on transmit and receive properties. I'm going to talk about impedance and impedance matching. I'm going to talk about the K factor and the effects of ground. At the end on the slides, there'll be 20 slides of references for people who want to study the subject. This will be a list of articles, books, and websites, and software especially, for people who want to do modeling. I won't brief that part in this talk, but it'll be on the slides for those who look up the hard copy, which will be archived. Linear cylindrical antennas. Dipoles are a member of the class of linear cylindrical antennas. A linear cylindrical antenna is a wire, a rod, or a tube driven at an arbitrary point, which we call a gap, somewhere along its length. The length is arbitrary, the feed point location is arbitrary, the length of the arms are collinear, but otherwise arbitrary. By collinear, I mean they're straight and in line. The cross-section does not need to be a circle. It can be some convex shape like a square or a polygon. It can even be topologically connected or disconnected, but you could have parallel wires that collectively form a parallel wires that are close together can still act as a dipole. An example would be a cage dipole. The currents are longitudinal. That's the key feature of a linear cylindrical antenna. The currents are longitudinal. They don't flow around the circumference. They flow along the length direction. A simple dipole is a linear cylindrical antenna. So it's an example of this kind of antenna, but it has additional properties. It is geometrically symmetric about the feed point. The arm lengths are equal. The current distribution is symmetric about the feed point. The feed point is balanced when the dipole is in free space. And when it is, a special case is a half wavelength dipole, which is called a Hertz dipole or a doublet. So if you hear those terms, Hertz dipole or doublet, it's referring to a half wavelength dipole. Okay, here's a few facts and fictions on antennas. We'll skip these. The symbol in the middle is my own symbol for a source. AC means a cat, but actually it's just, we'll just say the picture is a cat, it's the source, the AC source that drives the antenna. But there are some interesting facts. If a linear antenna is resonant, then its feed point impedance is real everywhere along its length. And that's true for dipoles because they are linear cylindrical antennas. Dipoles are resonant at lengths slightly shorter than an odd number of half wavelengths. And if a dipole is a half wavelength long, then its current phase is about 30 degrees everywhere along its length, where the reference phase is the feed voltage phase. Some fictions, however, and these are common, fictions or myths, is that half wavelength dipoles are resonant. And I've just stated to be resonant, the dipole needs to be slightly shorter than the half wavelength. Another fiction is that dipoles are 75 ohms. Well, no, that's not true. The impedance depends on the length of the dipole. In free space, a half wavelength dipole has real resistive feed point impedance. That's not true, but if the dipole is made slightly shorter than a half wavelength, it will be real. The impedance will be real. Half wavelength dipole is 50 ohms. No, that's not true. Feed point resistance of a half wavelength dipole depends on its diameter. A lot of people will think that's true. It's not. The reactance depends on diameter, but when it's a half wavelength, even the reactance doesn't depend on diameter. So for an exact half-length dipole, the impedance is the same regardless of the diameter of the dipole. So that's an interesting fact. And then finally, dipoles are anti-resonant at lengths slightly longer than an even number of half-wavelengths. And that one's not too important for us, but would be if we're working with end-fed antennas. Current, impedance, and resonant length. So let's go into the history of the dipole. I'm showing you a picture of the very first book on antennas. It was published in 1893. The author was Heinrich Hertz. Is titled Electric Waves, and in it is the theory of the dipole, and also the theory of spark gap transmitters and a bunch of other things. In cylindrical antennas, after Hertz, we developed a technique for analyzing antennas exactly. In mathematics, antennas are what are called boundary value problems. And a lot of people think, well, we just solve Maxwell's equations. And that's an oversimplification. When you analyze an antenna, you're not solving Maxwell's equations, you're solving a boundary value problem that satisfies Maxwell's equations. And so many, many attempts have been made and arisen over the years as to how to do this. The first was solving an equation called Pocklington's equation that was developed in 1897 after Hertz. The next software, for those that do antenna modeling, the next software originally was formulated on a numerical solution of Pocklington's equation. The next method that came along was the induced EMF method, developed in 1922, and the person whose name is most frequently attached to this method is P.S. Carter, who worked for RCA, and his paper came out in 1932, and then other folks have expanded on the Carter's technique. After Carter's work, the next integral equation that came along, better than Pocklington's equation, was the Hallen equation. And one professor in the United States, R.W.P. King, spent his entire career solving Hallen's integral equation. And he graduated many, many famous students who also worked on solving Hallen's integral equation. And that's the equation that allows you to analyze wire antennas, but it only analyzes wire antennas. Other antennas are of interest, and so Hallen's integral equation is kind of a relic of history now, but the work survives in the literature. All work since about the mid-1960s are a bit numerical, using computer programs, but the computer programs are based on techniques like the method of moments, which is a much more general and powerful method than these earlier attempts. And so we'll talk about that a little bit. I'm not going to brief these equations, except if you look at the very bottom, you'll see they all have the form of what are called linear operator equations, where you have some linear operator operates on some unknown function to produce a driving function. And the linear operator involves integrals and derivatives and stuff from calculus. And you don't need to know any particular integral equation, just this is the form. And this is this general solution for almost all boundary value problems that that you encounter in physics. And that is why the method of moments is so powerful. Jumping back to linear cylindrical antennas, I mentioned R.W.P. King. Professor King was at Harvard, at Cruft Laboratories at Harvard University. Here's a picture of him at his 100th birthday, the year before his death. He was the authority on cylindrical antennas. He spent, 60 years solving Hallen's integral equation with different techniques. He graduated over 100 doctoral students, many of whom are very famous. So the problem has a long history, and we'll show you some of the results of his work and compare it to method of moments in a moment. Sorry for the pun. The current distribution on antennas is almost sinusoidal, but not quite. And that is an interesting twist. In the induced EMF method, we assume that the current on the dipole is sinusoidal, but that's only an approximation. And what you'll find out in most of antenna analysis is there's lots of different approximations, and depending upon what level of accuracy you want, you'll either accept or not accept certain techniques of analysis and study. So here we see what the current distribution actually looks like. The Hallan solution, the Pocklington solution, and the sinusoidal solution. And the one that is the most accurate of these is the Hallan solution. The Hallan solution is the most accurate of these three. And what I'm not showing you is method of moments, which is more accurate still. Here's another picture, and this shows the, this may actually be method of moments versus the Carter solution. But you can see that the current distribution has a little dip in the center, and also it rolls off at a slightly slower rate than the sinusoid. So it's a little fatter. The curve's a little fatter, but it does go to zero at the ends, and that is a problem with some of the numerical methods, is that they don't get the current at the ends quite right. They get the current in the middle of the last segment if it's a segment model. Induced EMF method I mentioned, 1922, Carter published the big equations in 1932, and here they are. These are the equations that are published in the literature. They were used for years and years for the design of AM broadcasting towers. The monopole impedance is 1/2 of the dipole impedance. So for a quarter wave monopole over a perfect ground screen or radial system, you take these equations and divide by 2, and you get the resistance and the reactance. What I'll point out about these equations is simply the diameter of the wire, or the diameter effective radius of the tower, is the variable letter A, and it only appears in the reactance equation. Nowhere does the letter A appear in the resistance equation. So the real part of the impedance does not depend upon the fatness of the dipole, only the reactance. And moreover, the term that contains the diameter dependence goes to 0 when the length is a half integer multiple of a wavelength. So for a perfect half wavelength antenna, both the resistance and the reactance do not depend upon the diameter of the dipole. In fact, we'll see in a moment, that point defines a fixed point. Here's the actual evaluation of it. For the perfect half wavelength dipole, we get a resistance, and these are the theoretical resistance and reactance from the induced EMF method or the Carter method. And I've given it to you in many digits. Now, there's no practical application for all of these digits other than that we can compute them exactly. And these numbers are important if you're going to validate a numerical technique like method of moments. That's the only case in which you want to know what the exact answer is to validate your numerical method. In terms of measurement, you cannot measure anything this accurately. And so the various codes, NEC, FICO, WPLD, Hobbies, AWAS, all of them, we use these numbers as to determine one of the benchmark measurements. Here we see impedance of an antenna. Impedance is a complex number. It has a real part and an imaginary part, or a resistance and a reactance. The ARRL likes to show the graph on the left, where you see how the resistance and the reactance form a spiral, but sort of a triangular spiral on a semi-log plot. No engineer uses that data representation. Everybody nowadays uses the Smith chart, and they have in the professional literature for many years. But the Smith chart, the impedance of the dipole simply forms a spiral, concentric spiral on the Smith chart as you sweep frequency. So here we see for 2 antennas is frequency sweep from 1 megahertz to 30 megahertz for our 98-foot dipole. The resonant frequency is about 4.85 megahertz, but we're sweeping it up to 30 megahertz. So we pass through multiple resonances, and you'll see them on the Smith chart. As the curve spirals, it spirals clockwise as you increase frequency. So the curve starts at 0 frequency at the extreme point on the right, close to 0, the 0 impedance point, infinite reactance, and then the spirals clockwise, crosses the horizontal axis at the first resonance, and then spirals around, first anti-resonance, then the second resonance, second anti-resonance, and so forth as it goes around and around. So the Smith chart is the way we normally look at this because it has a lot of advantages from point of view. We can talk about the antenna's Q. A lot of people like to think of the Q as the ratio of the reactance to the resistance. That actually is not a good definition of Q for antennas. A good definition is based on field energy. The portion of the field energy that radiates to infinity divided by the stored energy. The stored field energy divided by the power is a good definition of Q. You can't determine Q for most antennas. You can't measure it from feed point impedance properties at all. For a dipole, the Q is a function of the geometry, and here's a good formula for dipole based on length, diameter, and wavelength. In this formula, C is the speed of light. So we have a dipole Q formula, and properly Q should be determined from the fields, not from the feed point impedance. And there's many papers in the literature, even in the professional literature, that try to come up with formulas for the Q of an antenna based on some property of the feed point impedance, either the impedance or its derivatives or functions of impedance and derivatives. All of those formulas are wrong, and I can give you counterexamples easily to every one of those formulas. So the only formula that is correct for the Q is based on field energies. Equivalent circuits. The circuit on the bottom left is the series RLC circuit. Every book talks about this as the equivalent circuit. This actually is a good equivalent circuit for an antenna at 1 frequency. It is not a good circuit if you want to have a model that fits or represents the antenna's impedance over a range of frequencies. It is the least accurate model. Slightly more accurate model for a dipole is on the lower right, which is the Chu TM10 mode model. And the difference is that the resistance has the inductor in parallel with it, not in series with it. An even more broadband model is the one at the top, which is one of my models, which adds 2 more elements to the Chu model. And that's a fairly good model. That's good for maybe 10% bandwidth, maybe 20% at the most. But whereas the series RLC model, resistor, inductor, capacitor model, that model is good for less than 5% bandwidth. So, but we can do better. We can actually construct models that are good over broader bandwidths, and I'm going to show that in a moment. Any of these models may be good enough. Certainly the Chu model and the one on the top are excellent if you're doing electrically small antennas and you don't need to go much above resonance. These models are quite accurate, whereas the series RLC is not accurate. These models are good if you want to build a dummy load, a dummy antenna, a dummy load that acts like an antenna. These circuit topologies are good ones for that. The series RLC is probably the least accurate. But you can build dummy loads that are good for electrically small antennas. We'll mention the word Darlington form. The circuits I just showed you are in Darlington form. What is a Darlington form? we're referring to Sidney Darlington. He was a famous network theorist at Bell Telephone Laboratories. He published probably the most famous theorem in the field of network synthesis back in the 1937 time frame. And it says that every passive impedance function can be realized, and we might substitute for the word realize, we can make it as a lossless two-port, meaning a network of inductors and capacitors terminated by a single resistor. So here's a picture. We have a lossless two-port. You can imagine inside that is some network of capacitors and inductors, ideal capacitors and ideal inductors. And we have one resistor that terminates the second port. And the impedance looking into that network is a function of frequency. It has a real part and an imaginary part. And what Darlington showed is that every passive impedance function whatsoever can be expanded in this form. And let me back up one slide. All of these equivalent circuits that I'm showing you are in Darlington form. They all have one resistor that's preceded by some simple network of inductors and capacitors. And where this gets important is when we get into formal impedance matching theory, that the Darlington form is a very important concept when it comes to impedance matching. So here, for example, here's an antenna. This is actually our 98-foot dipole. I haven't put all the values on yet. I'm going to put the values on in a moment, but here we see we're treating the dipole as a two-port. One port is the feed point. The feed point is on the left. What's on the right? Free space. Free space. So the dipole functions as a transducer that launches a wave into free space. And free space looks like a pure TEM impedance of 376.73 ohms. So we'll actually use this model in a moment. But let's look at some broadband models first. You can construct broadband models. This is an example. This one uses 4 stages. The whole theory of broadband impedance modeling is something I gave an IEEE talk on a few years ago. And that actually is on YouTube somewhere. You can, if you're interested in that. But here's our 98-foot dipole model. And this model is not a narrowband model. This is a model from 0 hertz to 30 megahertz. And the antenna is resonant at 4.85 megahertz. And this model is good through multiple resonances. And here's the example of the model. And the NEC reference data is the blue dashed line, and the equivalent circuit is the red solid line on top, superimposed perfectly. Here's an even more ambitious model. This is a 1 meter, or 2 meter rather, 2 meter long dipole. And this dipole, we're modeling it, even though it's 2 meters long, we're modeling it from 0 to 1.5 gigahertz through multiple resonances. This is the same circuit topology. I published this in 2007, and it's a modification of Foster's second canonical form, and 6 stages will cover the full band. And here it is from DC to 1.5 gigahertz. And here's real and imaginary parts. They track perfectly. You can't even see that the curves are overlaid. They overlay so tightly. Now let's talk about the K factor. The K factor, well, let me back up one comment here. If you wanted to build a matching network, one thing you can always do is you can use Foster's technique, not Foster's, Darlington's technique, to redraw this circuit topology to reduce the number of resistors down to 1. So if you apply Foster's synthesis theory, you can cast this whole network as a new network that has the same input impedance, but is a reactance to port terminated by one resistor. And the beauty of Darlington's theorem is he actually shows how to do it. He gives an algorithm. And that was a very hot topic in network synthesis theory. That was the era of analog electrical engineering, long before digital. Dipole resonance and resonant length. So an antenna is resonant when the electric field energy, stored energy, and the magnetic stored field energy are equal. Another definition of resonance is when the feed point reactance is zero. And I'll argue that the first definition is probably the better one, because you can make any antenna reactance zero by incorporating device or structure within the antenna itself. You can fool the formula. You can make the feed point reactance look like zero even when the fields are not balanced outside of the antenna, if you allow a matching structure to be integrated into the antenna. So we'll use the first definition of resonance. We'll use them both at various points. The question of resonant length was first pursued in the ARRL Radio Amateur's Handbook in 1947 and in the ARRL Antenna Book in 1949. And the ARRL published the curve on the left, and they published that curve in every handbook and every antenna book from 1947 to 1997. And then all of a sudden, mysteriously, starting in 1998, they published the curve on the right for another, quite a while, almost 20 years, from 1998 to 2018, and then they stopped publishing that curve. What this curve shows is the K factor. The K factor is the factor you multiply a half wavelength times in order to get the resonant length of the antenna. And so they're changing the K. Now, if you overlay the curves, they don't overlap. They don't overlay very closely at all. So this was a significant change in the published graph for the K factor. And this got me wondering what's going on. What is the K factor? The first thing I'll have to say is K is not a velocity factor. Everybody thinks K is less than 1, but it's a velocity factor. It has nothing to do with velocity factor. When we go in the literature, we find every author had a different idea of what this K factor was. And what's interesting is that the RSGB actually was the closest for many, many years. They published the curve. In this graph, if you can see it, the yellow dots and the magenta diamonds was the RSGB's publication. The ARRL's original curve is the orange curve at the top. And when I published it, when I looked at it, I didn't know where it came from, but it became evident it came from the the Blake King, Professor King's student Blake, solving Hallam's equation with a low order approximation back in 1942, obtained the orange curve at the top, and that's the one the ARRL published without giving attribution where they got the curve from, and published it for quite a while before they realized it was wrong. But when they realized it was wrong, they published another curve. The new curve that the ARRL published starting in 1998 was the black squares on the bottom. The black squares on the bottom was derived from method of moments calculation, probably done by L.B. Seebeck, W4RNL, but it was wrong in the opposite direction because, in fact, method of moments is not the best way to determine the value of K. It has some inherent limitations that Seebeck didn't understand. So they overcorrected, they published that curve, and then all along there was the very accurate curves in the literature due to, in the Antenna Engineering Handbook is Professor Tai, who wrote the chapter on wire antennas, and also Sergei Shelkinov, who was a mathematician at Bell Labs. Later, I went in more accurately and used the Carter formula and came up with a very accurate formula for the value, for the K function, which is what ARRL now published. So here we have the result. Shelkinov's 1941 approximation, the Ty-Elliott cubic polyfit, which is in the Antenna Engineering Handbook, first edition, Henry Jasic editor, and then my own quartic polyfit improvement to that, and then finally my solution to the based off of the work of Smith in RSGB, but ultimately traceable back to Carter, which is the most accurate. And we actually have an exact equation for that curve now, and that's published. So we know how to correct the length of a dipole. The only problem is, of course, the limitation is that this is for a dipole in free space. So if we want a resonant dipole in free space, we know how to do it. We will say that the explanations for the KYK is not unity are bogus. K is not a velocity factor, it is not an end effect, and is not due to a departure from sinusoidal current distribution. And there's good reasons why all of those explanations are incorrect. The induced EMF method does give K accurately, at least for the first resonance. So we'll stop with K factor at this point. There's more on it in the ARRL Antenna Handbook, the current edition, for those that want to read a little bit more about it. But the main thing is we've got a formula for K now that is exact, or very exact. Broadband impedance matching. Everybody knows how to do narrowband impedance matching, so I thought we'd say a few words about broadband matching. And there's a couple of ways to do it. If we're only interested in getting our SWR curve flat, we can use what's called a reflectionless match network. And there's a couple of ways to do those, and so I'll show one or two. We can also do a technique called non-Foster matching, and we can do it either at the feed point end, or we can do it not at the feed point. We'll do external matching, and I'll show an example of that. It's kind of funny or humorous, but it can be done. In other words, if you have a two-port, like your antenna is a transducer, you can put the match network at either end. You can put it at the source end at the port number 1, or you can put it at port number 2. And we'll show you what I mean by that. Here's a constant resistance network for a series RLC load. Now remember I said one of the models for antennas, narrowband models, is an RLC network. So we might think of that load as an antenna and the matching network as the figure drawn there. Notice it's got a transformer. We give the turns ratio of the transformer. We give the value of the two main components, the inductor and the capacitor, within the network in terms of the inductor and the capacitor of the antenna. And the resistor R inside the network equals the resistor R at the load. Let's see how this works. First, we're going to get rid of the transformer. Transformers are inconvenient and they're unnecessary. What we want to do is, if we want the antenna to match to 50 ohms, we'll just make the dipole have a 50 ohm real part by just making it a little bit short, make it electrically short. Instead of setting K to 0.95 and making the dipole, quote, resonant, we're going to set K equal to about 0.86, which makes the real part 50 ohms. Don't worry about the reactance at this point. And if we're doing monopoles, we'll do the reverse. We'll make the monopole slightly long. Instead of making it a quarter wave long, we'll make the monopole, or the vertical, about 0.27 wavelengths long. And again, the whole purpose is to make the real part of the impedance 50 ohms. Now the next thing we're going to do is we're going to add, for the dipole, we'll add a series inductor to bring the impedance up to the center of the Smith chart. And for the monopole, we'll do the same thing. We'll bring the impedance. We'll add a for the monopole, we'll add a series capacitor to bring the impedance down to the center of the Smith chart. So now we've got the impedance mapped to the center of the Smith chart. Now the next thing we're going to do is we're going to add the shunt network to create the 50 ohm constant resistance network. And so here's the example. For my 98-foot dipole, I'm going to add a series inductor and of 7 microhenries, and then I'm going to add the shunt or tank circuit and resistor. The resistor is 50 ohms, and the tank circuit has the values shown: 111 nanohenries and 12,000 picofarads, 12 nanofarads. And what this circuit does is it flattens the SWR curve to below 1.11. In fact, 5 to below 1.04 in this case. The reactance goes to essentially 0, just slightly positive or negative, but very close to 0 across from 1 megahertz to 8 megahertz. Now remember, this 98-foot dipole was resonant at 4.85 megahertz, but now its impedance curve is collapsed to almost a little point. There's an expanded view of the Smith chart on the right, and you can see the entire sweep from 1 megahertz to 8 megahertz occupies that little tiny dot just below the origin on the Smith chart. Well, that's kind of interesting. So we broadband matched the antenna, meaning we mapped the antenna's impedance to 50 ohms. We haven't improved the transmission bandwidth of the antenna. It still has a limit, but the impedance, the reflection, has gone away. So we used a reflectionless network to do that. Our transmission bandwidth is still about 2.1%, or our 3 dB bandwidth is about 6%. That has not changed. So this is the trick using a constant resistance network for matching. We can also do it with a stub. Here's an example showing it with a stub version of the same idea, where we'll map this first to 72 ohms and then use a transformer to pull it to 50. And it does the same thing. It maps the antenna to a little tiny impedance locus, even though this is a broadband sweep. And there we see the SWR is below 1.07. And the transmission bandwidth is 150 kilohertz. Another way to do matching is to put the antenna's impedance model in what's called Darlington form, and then just invert the reactance 2-port and put it in cascade. Put the inverse 2-port in inverse 2-port, that is to say the inverse of the reactance 2-port, put it in cascade with the antenna's reactance 2-port. And this is shown in this picture. And there's 4 ways to do this. They use negative impedance converters. And all of these methods work. They, in principle, give you infinite match bandwidth. And they give you the infinite match bandwidth without the transmission bandwidth limitation that you saw in the previous slide. This is quite interesting. And people have worked on this. Unfortunately, these networks are inherently unstable. So the big problem from a circuit theory perspective and circuit design perspective is that this theory is too ideal. You need to do something to make the circuit stable. And much of my work was on this very problem. And there's a number of papers in the IEEE literature on ways to handle this. But another thing you can do is you can do non-Foster matching, but you can do it external to the antenna. You can encase the antenna in a radome and make the radome out of the right stuff. And if you do this, you can get broadband matching out of an electric. So you can broadband match an antenna. And so I'll show an example of that in the next slide. This picture shows a monopole over a ground plane, but you could, in principle, if you had a dipole and you surround it by a radome and you make the radome of the right material, you can do matching. Now this is only of academic interest, so I'm showing it because it's external matching of the antenna rather than internal matching at the feed point. So here we put the match network on the antenna side, but we intersperse it. In the Darlington model, we put it between the terminating port resistance, the 376 ohm resistor, and the antenna reactance. And we do that by putting the radome around the antenna. In other words, the radome sits between the antenna and free space. And the radiation occurs outside the radome. Oh, I shouldn't. The term in the title, DNG means double negative metamaterial. We don't need to worry about that. But here's my example. My 2-meter radiator. There's a close-up view of my radiator. I hope everybody can see what it is. It was not very expensive. In fact, I have quite a few of them in my drawer of my desk right here. So if anybody needs an electrically small radiator, let me know. But here is the radome. The radome, instead of making the metamaterial out of electrically conducting spheres, I found that just the right size could be had in metallic foil balloons. And so here we have a radome, semi-circular or hemispherical radome shell made of electrically conducting spheres or quasi-spheres to impedance match that antenna. And we're impedance matching the antenna on the space side of the antenna, not on the at the feed point side. And again, this is the non-Foster matching idea, but a different variation on it. There's a picture. It looks very pretty. However, don't try driving more than about 2 miles an hour with this thing on the roof, or it will disturb your performance. So with that, let's get back to radiation and dipoles. Radiation, AC and DC steady state currents produce magnetic fields. However, only AC currents produce electromagnetic fields that radiate. In electrical engineering, we say time varying current produces radiation. In other words, time varying current is the cause of radiation. In classical physics, we say the cause of radiation is the acceleration of charge. Charge that's accelerating or decelerating creates radiation. Well, charge that's accelerating or decelerating, an engineer would call it time varying current. So we're really saying the same thing. In modern physics, we might say that photons, the radiation is made of photons, and we can talk about the photon rate. So we're not going to get into this much, but I will say that the photon rate is rather substantial. A 100-watt, 2-meter transmitter is radiating photons at the rate of 1 billion photons per second. 1 times 10 to the 27th power photons per second. So that's what your 2-meter rig radiates if it's radiating 100 watts. That's a lot of photons. We'll get back to that in a moment because photon explanations become interesting, particularly when we talk about receiving antennas. Here's a myth about wave propagation. I've already mentioned it, so we'll skip it. Coordinate systems, spherical coordinate systems. We have distance from the origin in 2 angles, a polar angle and an azimuth angle. In ham radio, we usually use the elevation angle, and the azimuth angle is the compass azimuth angle, measured clockwise from north, north being the y-axis usually. In any case, we don't need to worry about coordinate systems much. The letter R here simply means the distance from the origin in the spherical coordinate system. Theta means the polar angle. And so we have equations for infinitesimal dipoles in free space. These are the field equations. So we have this in closed form, and this is all worked out in the antenna literature. So for infinitesimal dipoles, we have these formulas. We can derive more complicated formulas for half wavelength dipoles. But at some point, one decides that mathematical analysis is too complicated to do by hand or too laborious, and we nowadays just put everything into the computer. But one thing you do get out of these equations is you get Heinrich Hertz's drawings of the electric fields of a dipole. And these are instructive, and Heinrich Hertz did these drawings in 1888. I cannot believe that he drew these very beautiful and accurate pictures in 1888, based only on the mathematics with no computer help whatsoever, but got the full explanation of how the fields expand and go outward. You'll notice on the left is a sphere, or a circle rather, and inside that circle the field lines are concentric, closed on themselves, and outside the circle the field lines break away. And that diameter of that circle is the radian sphere. And here it is again. This is a modern computational technique, and this dipole is a half wavelength, not infinitesimal. But you see the same picture. Inside are the near fields, inductive near fields, and they terminate on the wire. They actually terminate on the metal conductor, and then as things evolve, they break away from the conductor, and then they go out through this phase where they are closed on themselves, and then further out so you have sort of an inductive near field, and then you have a near field, and then you have a far field. And so you can see all of them in this picture. This picture is actually, I believe, animated in my PowerPoint. And I don't know if Zoom is showing any of these field animations.
Yes, that's fine.
You can see them?
Yes,
okay.
Absolutely. They're very good.
These little animations are all over the web. You can every website has these little field animations. Everybody's got their own version. They're pretty to look at, but you can see how the field lines start on the antenna, expand outward, break away, and then travel off into space. One of the things you can get when you have the expressions for the electric and magnetic field is you can get power flow. The power flow is defined by something called the Poynting. Poynting was another physicist, a contemporary of Maxwell and Hertz. The Poynting vector describes the direction of power flow in space. But because power is complex, it has a real and an imaginary part, we can resolve the Poynting vector into a real power flow vector and an imaginary power flow vector. And the imaginary power flow vector corresponds to reactive power. Now, for dipole radiation, the real Poynting vector is irrotational. It has no solenoidal component, so the power goes off to infinity. And that's what we call the far field. The power that goes off to infinity from a transmit antenna goes all the way to the far field. It's possible to have other antennas that don't have this property, where the Poynting vector, the real part of the Poynting vector, is solenoidal or has a solenoidal component to it. And in that case, the energy is, the real power is sort of swirling around in space. And that's something you can sometimes find in antennas that radiate what's called orbital angular momentum. But we won't worry about that. That's new stuff in antenna, is orbital angular momentum. For dipoles, the gain of an infinitesimal dipole is 1.5. I've already mentioned that. In decibels is 1.76 relative to isotropic, or negative 0.39 in dBd. I prefer not to use dBd because it's imprecise. We don't actually have an exact formula for the gain of a half-wave dipole. Like we have a nice formula for the impedance, but we don't have a nice formula for the gain that has the precision. So every different technique for computing the gain of the antenna, you get very differences in the hundredths or even tenths of a dB, and so therefore it's not a good reference. The isotropic dipole is rock solid, so that's the reference, and everybody uses it. But anyway, we can compute the pointing vector flowing out through a sphere. We can actually calculate the pattern and from the pointing vector and get the gain pattern. Gain is not just a number, it's a pattern, the gain pattern, but it has a maximum. And when we talk about the gain of antenna, we're usually talking about the maximum gain of the antenna rather than the shape of the pattern. But the shape of the pattern sometimes is called directivity. If the antenna is lossless, the gain pattern and the directivity pattern are identical. If you include the losses, any losses, then we have the gain has the same shape, but it's less than the directivity. So let's look at some patterns. And here we have a half-wave dipole pattern compared to isotropic, and we have this figure 8, and it's a figure of revolution, so you can think of it as a donut. And so we have the isotropic spherical pattern, and superimposed on it we have the figure 8 donut pattern. And we're going to look at these cross sections. And so here's the gain pattern of the quarter wavelength dipole. And I'm going to slowly increase through a series of images, increase the length of the dipole and show you what happens. As we go from a quarter wavelength to a half wavelength, notice that, look at what happens. The donut gets a little bit more elongated or squished. As we go from a half wavelength to 3/4, it gets squished more. It goes out more. That means there's more gain on axis. What I mean by axis is horizontally. It's omnidirectional. So in the omnidirectional, or in the plane direction of maximum gain, the donut gets squished, the gain increases. We go to one wavelength. We go to 1 1/4 wavelength. At this point, we start seeing little side lobes form. And as we go above 1 1/4 wavelengths, or 5/4 wavelengths, suddenly the main lobe collapses and the side lobes pop up. And as we go beyond a wavelength and a half, side lobes the former main lobe disappears entirely, and the side lobes get a little longer and longer and longer as new side lobes pop up, and then it collapses again. And now the new side lobes are biggest, and they get longer and longer and longer until they collapse. And this goes on and on. And so what we have, if we graph this, is a plot of the dipole's directivity or gain as a function of its length. And we see that the dipole gains for infinitesimal dipole is 0 or 1.76 dBi. And for the half wavelength dipole, the gain is 1.64 or 2.15 dBi. And as you increase it, you get up to a maximum at the 5/4 wavelength, where the gain is 3.3 or 5.18 dBi. And then it collapses and it proceeds to grow again. And we have the second, and then it collapses and it grows again. And so this goes on and on and on as you get side lobes. And so this is a very interesting property of the dipole pattern, that you get all of these lobes depending on length. And so that's why frequently for monopoles, we'll make them 5/8 wavelengths long, 5/8 wavelengths long, half of 5/4. And the reason is we want the monopole over the ground screed to have high gain in the horizontal direction in an omnidirectional pattern. Now we're going to shift to well, let me first point one thing out. I've already said that as the dipole shrinks to 0, the gain doesn't go to 0. It goes to 1.5. So as the dipole shrinks, the gain decreases, but it doesn't quite disappear. Well, this is something kind of like the Cheshire cat, who slowly vanishes, but his grin remains. As the cat slowly fades out, the grin remains. As the dipole shrinks to 0, its gain remains. Doesn't quite go away. With receiving antennas, we can talk about excuse me. This quantum brain teaser. For receiving antennas, the photons are coming into the antenna. And so the question is this: if the dipole size shrinks to 0 and the photons are incident on the antenna, they're coming in from far away. So you've got all, you can think of all these photons streaming in, but you let the dipole size shrink to 0, how can the dipole capture any photons? The target becomes infinitesimal. Don't all the photons miss the target if the target goes to 0 and is infinitesimal? And yet we know that the receiving antenna has the same gain as the transmitting antenna, so the receiving antenna's gain doesn't go to 0. And it turns out its gain doesn't go to 0 and its capture area don't go to 0. So this is a mystery. What are those photons doing? Why are they able to find the antenna even if the antenna is invisible? So I'll leave you with that question for the moment. We have these nice equations called the free transmission equations that explain the receiving properties of antennas and relate receiving and transmit properties. We don't need to know that too much. But we'll come back to this intriguing question. The field energy and the momentum follow the pointing vector. The pointing vector steers into the antenna and hits the antenna. If you look at the streamlines of the pointing vector in the vicinity of a receiving antenna, they stream into the antenna, they hit the antenna, and they actually hit the antenna at the feed point where the antenna absorbs energy from the incident field. That's magic. How do the photons know to do that? Or maybe the photons don't follow the energy and the momentum. The question is, do the photons travel on curved paths? And if so, how do they know what paths to curve along? And we'll just leave that as the dilemma. Classical physics gives us the method of analyzing these antennas and calculating reception exactly. Modern physics has a trouble because we can't get beyond the photon travel explanation and this mystery of how the photons travel. So we have this, I'll call it a professional discussion. Engineers will calculate, physicists can pontificate, we can disagree on what's really going on, but in the end, the Cheshire cat remains. The gain does not go to 0. In fact, the receiving gain goes to the numbers I gave already. We've already said this. Effects of ground. Okay, we're up to 1 hour and 10 minutes. This will a little bit more and then we'll stop. Ground effects. Dipoles can be vertical or horizontal or inclined over ground. So when you introduce ground, you no longer have a dipole in free space. You have a dipole and something else, an object, the ground. And the dipole can have an orientation relative to the ground. But if any part of the antenna is near the ground, then the current distribution is generally affected. And if the current distribution is affected, then other antenna properties will be affected. And that includes the impedance and it will include radiation behavior. Generally, what I've discovered, and I think all engineers know this, is that when you bring in an object into the vicinity of a dipole, the impedance is affected first. It'll show up as a mismatch on impedance. The pattern is very insensitive. Pattern will eventually be affected if you get the object close enough, but pattern is insensitive. Impedance, on the other hand, is very sensitive. So the effect of ground on a dipole, if the dipole is above the ground, the pattern will be changed a little bit, but the basic pattern may not change much. I'll have more to say on that in a moment, but the impedance is definitely affected. The old methods of analyzing the affected ground relied on lots of mathematical techniques and approximations, but we generally made strong assumptions about the shape of the ground. The ground had to be infinite, flat, smooth. In other words, we model it as an infinite half space, the infinite half space model. What we did not allow is the ground to be finite, irregular, bumpy, or have complicated material constants. Of course, modern numerical software lets us get around all of those assumptions. We can actually model ground fairly exactly if we want to with our antenna modeling programs, if you use the correct program. Not all programs could do this. But the material assumptions that are simple are perfectly conducting ground. Perfectly conducting ground has infinite conductivity. It's basically a mirror or a metal sheet that goes out in all directions. For those kind of grounds, you can do all your analysis in closed form, mathematics equations, and you don't really need any computer modeling. But when you get to realistic cases, you do need computer modeling. Infinite half-space theory is in the literature. The big names were Sommerfeld, who solved the infinite half-space problem as a boundary value problem. Originally, he actually did it twice in 1909, and that work had an error. He didn't even know that there was an error. He redid the work in 1926 and published it again. The error was gone. Unfortunately, the earlier work survived, and there's a lot of subsequent work that was based on Sommerfeld's original equations that keep the error. And so you have to be careful when you're using Sommerfeld's theory to make sure you're using the 1926 version and not the 1909 version. It's important if you're reading books on the subject. Norton was another big name. Weil is the person who showed that Norton and Sommerfeld were correct. That the second solution was the correct one and not the first one. Van der Pol-Nissen confirmed it through other measurement techniques. Rice and Wise confirmed the mathematics. Burroughs, Booker, Clement, Baukamp, and Waite have all published on this. Waite has published the most extensively of any recent author, but he died in I believe it was October of 1998, and so he's no longer with us, but his work survives and is probably the best treatment in the literature for anybody that wants to understand how to model ground using the infinite half-space approach. But numerically, we can allow ground to be not infinite, non-flat, and not smooth if we use numerical methods. So let's look at that. Here's our choice of different methods for modeling the ground. With irregular models, we use actually model the geometric shape of the ground using a topographic database data, and we can even put trees and landscaping in if we want. I spoke on another talk on how you model trees quite accurately. Or dielectric objects more generally. But when you're modeling dielectric objects, you can model them through their surface impedance, or you can model them through an exact integral equation. So these are all techniques for modeling the ground. The earlier methods are at the top. More recent modern numerical methods are at the bottom of this tree diagram. The effect of ground on dipoles is that the impedance depends upon, and this is a horizontal dipole, the impedance of the horizontal dipole depends upon the height in wavelengths above ground. And here I'm only showing the real part of the impedance. I'm not showing the imaginary part, but it also can be graphed. So we see that for the perfect electrically conducting ground, the impedance goes to 0 as the antenna height goes to 0. And for real ground, it does the opposite. It zooms up to about 90 ohms. The exact value and shape depend on the ground material constants. On the right is a more elaborate graph of the same thing from a textbook. One of my favorite textbooks on antennas is Konstantin Balanis, Antenna Theory. Balanis is professor of EE at Arizona State University, and his textbook is the successor to Krauss's famous book on antennas that's used in all university classes. And so his book is in the 4th edition. And this graph is taken from the 4th edition, which is 2016. I think the graph is the same in the earlier editions. But here we see for different ground conductivities and a dielectric constant of 10, we can see how the dipole's resistance curve lifts or rises and varies. Actually, we've got reactance on that curve too. He's got both. The Balanis curves, you'll see the curves for X and the curves for R are both there. So we have resistance and reactance graphed. So that's another thing. And you can compute these things using method of moments for arbitrary ground, for flat ground, infinite flat ground. And that's what these curves are for, infinite flat smooth ground. Solutions to the half-space problem. The field patterns, when you're over dielectric ground that is conductive, the field patterns tend to lift. So instead of the pattern having its maximum at 0 elevation, the patterns tend to lift, and this is a problem. And of course, people spend a lot of time trying to figure out how to get the patterns to unlift, how to get the patterns down. For good DX, we want the radiation to be around 5 to 20 degrees. We don't want the pattern to be shooting off at 45 degrees into space. For near vertical incident skywave, we want the opposite. We want the pattern to lift. We want the pattern to actually concentrate its energy above 45 degrees elevation angle. And so that, of course, is much easier to do. Just put your antenna close to the ground and the pattern will lift, although there are much better ways to do it to get high gain from or near vertical incidence antennas. But this is for a vertical, not a horizontal dipole, but a vertical dipole. And this is a vertical half-wave dipole above ground. And so you can see how the pattern lifts. And this is a well-known phenomenon. You can model it in neck or easy neck, 4-neck tune, any of the neck engines, or Mana-Gal, based on a mini neck. We'll all do this for you. If we want to model the ground as a surface, then we have to use a more powerful technique. We still use the method of moments, but we have to model the surface rather than a thin wire model for the ground. And these programs exist. They're embodied in computer programs, Pico, Whipple-D, and the inexpensive one, Hobbies, which was available, all did this very nicely. And there you just model the ground as a sheet, and it can be a bumpy sheet. You define its geometry and give it the constants and let the program do the analysis. So we'll show an example. This is an example of modeling the ground as not flat, not infinite, and not smooth. We have irregular ground. This is topographic model. My QTH is somewhere in that picture. You see the mountains or the hills in the background. Those are the Santa Cruz Mountains of California. and what you see is sort of looking, this view is looking to southward. We can take that whole ground model and import it and analyze it. Another one that we can analyze is ground that is not infinite. We can even make the ground round. Well, I have a flat ground. The Earth is not round or flat, is it? Or maybe it still is to some. But the Earth is round, so why not make the ground round? Well, of course, there's a good reason. You have to mesh very finely. But I did do an analysis for a mesh for a small planet. I put a 160 meter antenna on a small planet and gave it a spherical shape, and I even put a molten iron core in the middle, and I made the rest of it out of seawater or desert sand, and so computed the. So here we see this is not a dipole. This is a monopole. This is a 160 meter band monopole, which is the blue line at the top. I modeled it as Arizona desert sand because Tom Schiller, N6BT, wanted to know how his monopole works in Arizona. So we made it out of desert sand. But to be creative, we decided we'd put 4 redwood trees in around the 160 meter antenna. The 160 meter vertical was taller than the redwood trees, but we put 4 redwood trees in. I don't know why there would be redwood trees growing in Arizona sand, but this was just to show that we could do it. We calculated the patterns for this antenna. It took 2.5 minutes on a 12-core Windows 10 machine to calculate patterns, but all 12 cores were maxed at 100% for about 150 seconds. So the fans on the computer went into turbo mode, and this is not something you want to do on your computer unless you have good fans that are reliable, because you can cook your CPU doing this kind of stuff on a desktop. Here we have an animation. I hope the animation is showing. We can see the fields being launched from the monopole and being conducted, the ground wave being conducted around to the bottom of the planet. And at some point near the bottom, the fields actually detach and shoot off into space. So we were able to get both the fields and the currents. The current in the wires, the currents in the earth, the currents in the trees, fields everywhere, and look at the patterns. And we can actually got the patterns. Of course, most people would look at the patterns first. So let's look at the patterns. And what's interesting is that this vertical monopole radiates more energy in the sort of the lower, below horizon, due to this wave traveling phenomena, the ground wave being guided around the planet and then the field lines detaching. You end up with a funny pattern. And more energy is going down than up. And that calls into question, what is it that you really want to know? Do you want to know what's happening at infinity? Or do you want to know what's happening at some other point on the planet? Not at infinity. And so we'll argue that the far field pattern may not even be the most important thing if you're doing this type of modeling. So you have to ask the right question in order to get the answer that you want. Transmit antennas. Antennas, in this talk, have all been dipoles, straight line dipoles. But let's look at some other wire antennas just to put dipoles in perspective relative to other antennas. Because an antenna can be made out of wire and still not be straight. The wire could be bent, it could be curved, it could bifurcate into multiple wires. It could be not even topologically connected. You could put a segment of wire in front of a segment of wire in front of a segment of wire and create a beam, a Yagi-Uda beam. So let's look at some curves that show the possible gains. These are the maximum gains you can get out of a transmit antenna. And what we see for the straight element Yagi-Uda antenna we see the green curve on top. And that green curve shows the maximum gain you can get for a given amount of wire. So our horizontal axis is the total amount of wire that's used in the construction of the antenna. And so we see our dipole curve is the red curve, which we saw previously. It's shown at the bottom. And I've only graphed it out to 3 wavelengths, but it doesn't go up. It hits a maximum and then it sort of oscillates around. That's our dipole, our dipole in free space. If we have a V-beam antenna in free space, there we have 2 arms. It's a dipole, but with 2 arms that are not collinear, but are form a V. And if for every length we choose the angle of the V that gives highest gain, then we get this gray curve. So the gray curve shows the amount of gain, maximum gain you can get out of a V-beam in free space. And we can see that you get a lot more gain than you can get from a horizontal or a straight dipole in free space, but you cannot get as much gain as you can out of a Yagi-Uda, where the wire is arranged differently. You take the length of wire and cut it into pieces and put them in the right places. You can get more gain. But then we have another curve here, which hams have never seen before, which I decided was of interest. What happens if we don't make the dipole straight? And we don't even make it out of straight segments. Let's suppose we allow the wire to be symmetric, fed in the center, but the 2 arms are allowed to curve, follow a curved shape. How much gain can we get? Can we get more gain? Then we can, and the answer is yes. We can get more gain than a straight dipole. So by letting the arms curve and bend, we can get a lot more gain than a straight dipole. We can get more gain than the V-beam. And if you let this go on long enough, out to wavelengths above about 5 wavelengths, your shaped coplanar I'm calling it a dipole. It's not a type dipole. It's just a shaped, optimally shaped 2-armed wire with an optimum curve. But you'll get more gain than the beam. So you can beat a Yagi-Uda with the same amount of wire if you arrange the wire differently. Rather than cutting it into little straight segments and setting it up like a Yagi-Uda, you just keep all the wire connected, curve it in the proper curve, and make it long enough. You can get more gain than you can out of a Yagi. So you can get high directivity and high gain out. That I thought was something interesting because nobody's ever built an antenna like this, probably because nobody's ever talked about it before. And I gave a talk on that at Pacificon, ARRL Pacificon in, I think it was 2004, October of 2004. Okay, my last slide, I think this is probably my last. Receiving antennas, we have, when we're talking about receiving antennas, we're not interested in gain, we're interested in noise figure. Actually what we're interested in is signal to noise ratio, or signal to interference plus noise ratio, SINR. Those are the correct metrics for receiving antenna. Gain is interesting, but it's not the primary determining performance factor for a receiving antenna. So here I'll simply present some results that have been determined for comparing vertical and horizontal dipoles and loops at HF frequencies, and what the noise figures are that are achievable for antennas over average soil. In this case, these particular curves are, the antennas are 2 meters above average soil. And we're dealing with dipoles 2 meters long and loops 1 meter long, located 2 meters above average soil. And the external noise is galactic noise coming in from the sky noise. And we find that we can rank the order of these antennas. We can rank the antennas in order of noise figure. So at low frequencies, the order is different than what the order is at high frequencies. So at low frequencies, your vertical dipole has the lowest noise figure. So it will give you the highest SNR at the receiver. At low frequencies, your vertical dipole is best. Your horizontal loop is the worst. It shifts as you go up in frequency. At high frequencies, the ordering changes, and what we discover is that the horizontal dipole has the lowest noise figure at high frequencies, and the vertical dipole comes in second place. And again, the horizontal loop is the worst. So this is very important if you're designing antennas just for receiving. And in a ham station, you actually can have a separate antenna for transmitting and receiving. So you could actually have one antenna optimally designed for transmitting and another antenna optimally designed for receiving, and to maximize SNR, and consider doing that as another way to boost contest performance. Okay, I think we're at the end. Just a few final summary words. Simple dipoles can be analyzed in closed form, and by simple I mean dipoles in free space without the complications of other nearby objects. In practice, objects near an antenna affects its performance, and these objects come in various guises: parasitic radiators, fences, feed lines, guy wires, buildings, PVC pipes, houses, trees, people, animals, ground, and terrain. All these objects make the problem of antenna modeling and analysis too complicated for closed form mathematical type analysis. But the good news is the numerical methods now can deal with all of these kinds of issues. And so you can make very detailed models and study them numerically. And you just have to make sure you use the correct software, or the best software that has all the features and can do the job. You can even model irregular terrain. And with that, we'll hit the resources. I'll just flash through the resources so you know it's here. I'm not going to talk about them. But we've got a big bibliography on books on electromagnetics and electrodynamics. And I make a distinction. You know, if you're taking this class from the electrical engineering department, the book will be titled Electromagnetics. If you're taking the same class from the physics department, it'll be titled Electrodynamics. What are the differences? It's the same subject. Well, there are a few differences. The physics books always have a chapter on special relativity. The electromagnetics books always emphasize duality, and they'll usually, the better ones will use vector magnetic potential and vector electric potentials. So, but that is useful because that makes the mathematics, the setup of problems, the equations simpler, and so the analysis comes out faster and easier. So there are some very fundamental differences between these books, even though they're talking about the same subject. Any discussion of quantum physics may be present in the books on electrodynamics. There will be no discussion of quantum physics in the electromagnetics books. It's purely classical physics. Okay, so we have basic books, we have advanced books that you'd use at university graduate level. We have a ton of papers on computational electromagnetics, which got its start back in the mid-60s, and then has slowly gotten better and better. Insulated wire, if you want to model insulated wire, there's some very primitive methods, but there's also a sophisticated method that I just published in QEX in November, December of 2024. The difference is a sophisticated method allows multi-layered dielectric, and the dielectrics insulations don't even need to be dielectric. They can be magnetodielectric. So you can have composite, magnetic, electric, partially conductive materials coating a wire, and you can analyze their effects. You can even analyze metal cladding, a wire that's one metal clad with another metal. So insulated wire models, I'm coming out with a new article soon that'll extend that to lossy models. The article that's published covers the lossless insulation case. So you might be interested in that. Also, those models have been compared against the NEC 4 models, and measurements have shown that these new models are more accurate than the computational models built into NEC 4. This is demonstrated with the latest version of EasyNEC, uses the new insulation wire models, and that running on NEC 5 is far more accurate than NEC 4 and agrees with measured antenna data. Insulated wire. So then we also have ground, flat ground, infinite ground. For those that want to review the theory on infinite half space, it's all here. Irregular terrain analysis. A lot of hams use the HFTA code that ARRL distributes. Dean Straw, N6BV, wrote that code. It's a ray tracing code, but a much more accurate method, if you have the computer horsepower, is to simply model the ground. Model the ground as a dielectric surface and mesh it and include it as part of your antenna model. And that's part of what I was showing earlier. The first person to do that was Keith Snyder, presented it at the ACES conference in 2006 using my antenna QTH data, and then we represented it a few times. Modeling trees, the latest paper on modeling of trees, the ARRL had a nice paper in QEX by SWIAC and Quick in April of 18 in QST. I improved that on that model significantly, and then went on to show how we could make Yagi arrays out of dielectric rods and basically use a forest of trees in the proper configuration. So basically landscaping your yard by growing your trees in the correct places, you can make a very fine antenna. Very stealth antenna too. Neighbors will not know what you're doing. Optimization and shaped antennas, we talked about curved antennas. So there are some references on curved antennas. And then antenna modeling software. The best thin wire code at present that you can buy is NEC 5 and also ANSOFT. They have slightly different features. They're very accurate. Neither one has all the features you would want. For the price, I would recommend NEC 5 together with the EasyNEC graphical user interface, the newest version, and the AutoEasy program that works with EasyNEC. Those three together form an inexpensive combination that handles almost all the problems that you might want to encounter. It will not do the irregular terrain, however. For that, you need Whipple-D Hobbies or FICO. Hobbies, I won't talk about Hobbies. It's no longer available, but if anybody is a cracker who wants to assist the disassembly of machine code in the object code and help me with unlocking the code, I do have executable code. Licenses that were issued are no longer being issued, and all the licenses that were issued expire in 2030. So we have a few years to figure out how to crack that code, or it'll be gone forever. So let me know if you have a software expert who is an expert at cracking. CAD geometry for the surface meshing codes, antenna books for professionals, antenna books for amateur radio operators, some books that I like, recently published, and books for impedance matching for both beginners and experts, and finally some general reading, books on history, mainly history of technology, either television, radio, electricity, or circuits. So with that, I think we are reached the end, and I certainly reached the end of my time, and I appreciate your indulgence this long. Let me turn the floor over to our moderator and see if there are any questions.
Okay, Steve, well, thank you very much. For me, I know you did say you were going to simplify a little bit, but that was quite an in-depth talk. But lots of people watching live, many more will watch the recording, of course, as well. And if you'd let me have maybe a list of some of those, the particular handful of the books and resources that you'd recommend, and I'll make sure they're put onto the RSGB archive where this video will be available to watch again in the future. So if you've got any questions or comments, though, you'd like to share and haven't already done so, please do it now on either YouTube chat or BATC messaging. And please don't forget to include your first name and your call sign, if you have one, within every message. Steve, I was taken by what you just going through those books, and I was looking at the sort of oldest books, which I think were sort of 1950s. That I could see anyway, the references. But taking back into the talk where you talked about Hertz, who was so forward thinking that in 1888 he drew those drawings of the electric fields. It's incredible because he didn't have any real tools or instruments that we have now, did he?
Yes, he must have had a French curve and spent a lot of time. It's amazing he was able to draw those curves based only on the equations. I look at those equations and I think, wow, that looks hard. I would have to immediately go to a computer to draw them, and he was able to do it with whatever computational techniques he had available. I'm sure he had very good insight, very good intuition, and very good insight.
Yeah, as you say, I mean, all of us now, I think, would certainly think about using a computer to model something like that. Or if we're a bit old school, we might try and use oscilloscopes or spectrum analyzer or something. Because none of that was going to exist, 130 years ago, roughly? Amazing, isn't it?
Yes, and Hams did not use spectrum analyzers until recently. It was the nano VNA, probably within the last decade. Actually, since about 2000, when amateurs finally started realizing the nano VNA existed and using it for impedance measurement. Before that, we used antenna analyzers, and before that, they were RLC network units.
Indeed. So,
instrumentation has really improved.
Incredible. Well, as I said to you watching at home, please do, if you've got any questions for Steve. Steve said he was keeping some of the levels back a little bit, so if you've got an in-depth question, please, this is the perfect time to ask Steve it now. We have got one question that's come in so far. It's from Russell K6OIK, and he's asking, how do you design tree antennas? Now, I know you showed some books there, but can you just go into it in a fairly basic way, how you go about designing tree antennas?
Yes. In modeling antenna trees, we usually model just the trunk. We don't model the foliage, although we can model the foliage. But usually the trunk of the tree is sufficient, and if you can model it. So we model the trunk as a dielectric cylinder, and it's tied into the ground. So we're going to model the tree as a dielectric cylinder that's standing on the ground and electrically connected to the ground. And if we put in, we can think of it, if we make it like somewhat near, say, a quarter of a wavelength, we now have got a monopole or a vertical, but it's not made of metal, it's made of wood. A living tree has got a layer under it called a cambium that is full of sap and is conductive, and so the tree actually will conduct currents up and down, or in any direction. The difficult part with trees is coupling into them. there were papers, even in Scientific American, by George O. Squire, back in the, I don't know, a long time ago, 1920s. And I think he was in the British Army, showing how you could hammer nails into trees and excite them directly. But that actually is a technique we don't use. It's not good. The trees don't live very long. If you use it that way, you'll kill the tree and then
Sure.
lose your antenna. So the way we excite trees now is with a coil. A coil is similar to a Rogowski coil, but it's a coil that wraps around the tree and inductively couples into the tree. So we're coupling into the tree. In the language of modeling, we're exciting the dielectric column with a magnetic frill. We call it a magnetic frill, but in the implementation, what it is, it's a coil that's wrapped around the tree like a helical coil slinky going around the tree, and we drive the slinky, and then that couples into the tree, and we can couple out of the tree. So that's our driven element that will just be the vertical monopole driven near its base with the coil. And then if we put another monopole, it could be metal or another tree, the right distance in front of it, now we've got a director. And we can put another tree behind it and have a reflector. So we can have a reflector, a driven element, and a director, and we can have another director. So in the simplest case, we might just have 3 trees. Or even simpler case, we might have 2 trees. You might have a reflector tree and a driven tree. You can also just use a regular, if you have a portable vertical, you can put the portable vertical in front of a tree and use the tree as a reflector. Now, how do we analyze all this? Well, we analyze it using the antenna models that are presented in the paper that's backed up to trees. That first bullet item there, grow an antenna from seeds, ARRL Pacificon seminar, October 2023, and the slides are archived, so you can download those slides and see how it's done. To do the calculations on that presentation were all done in 4NEC2, using the NEC2 engine. Of course, you're welcome to take the models and rerun them in NEC5. You'll get more accurate results. Or if you have a surface model, meshing model, you can rerun them in Hobbies or FICO and put in a more accurate ground model and run them again. But the basic principle is you building a Yagi by putting spaced elements designed to particular lengths and particular spacings, and making an array of verticals in a line. All of them are parasitics except for the driven element. That's the basic idea. But the techniques can also be used for modeling a shrub. If you had an antenna and you had a bunch of shrubbery around it, if you could get the material parameters for the shrubs, you could model the shrubs and put them into your antenna model and see what effect they have. The reason I got interested in tree antennas was people were interested in what happens if you suspend a dipole between 2 trees or a sloper against a tree. Does the tree absorb power? Does it reduce your performance by adding extra losses? And I showed it can do both. Depending on geometry, you can use the tree to improve your antenna's performance, or the tree, conversely, if you don't exploit the geometry, the tree can have either a helpful benefit or it can hurt your performance. It's probably more likely to hurt your performance unless you specifically design it the other way around. So trees should not be thought of as your enemy. Trees can actually be exploited and can be very useful.
I mean, I've nothing like the knowledge you have, Steve. But to me, you mentioned the sap that goes around in a living tree. But wouldn't it make quite a lot of difference depending on what time of year? In other words, whether it was wet or whether it was dry? Wouldn't that make a huge effect on the conductivity of the tree itself?
Yes, the trees tree material properties have been published, and they do depend upon the species of the tree, the nature of the forest environment, whether it's dense or individual isolated trees, and also time of year. So all of those are variables, and those are things you need to know. So actually, if you plant your seed, you grow your trees, you design it so that when the trees reach a mature height, you'll have an antenna that'll work well in a particular direction at a particular season, perhaps. It's hit and miss. Of course, if you're simply using the tree as a reflector and you have a portable vertical on a tripod, you can slide the tripod's position forward or aft to get the correct performance, and thereby compensate for the change in property of the tree. But you're correct in saying that, yeah, everything is based on assumptions that the geometry and material properties are known in advance.
It's fascinating, I can tell you. Next time I see 3 trees in a line, I'll look for a bit of coax coming from them or something like that, or a twin feeder. So I hope that helps you, Russell G4IKL, who asked that question. Now we have a question from Andrew KR6DD, who says he's a long-time admirer of your contributions at San Francisco Bay Area radio clubs and Pacificon conferences, and asks, or mentions really, that a ham radio friend about 40 years ago coupled into a tree and just used a nail hammered into it, and he said that worked quite well.
I'm sure it can. If
Maybe he was just lucky, I guess.
Well, if you're doing this in California, be aware that the Sierra Club takes a dim view of hammering nails into trees.
Yeah,
and an even dimmer view of hammering the nail into the tree and then attaching wires and driving RF current into the tree. That is, it's nice that there's an alternative method.
I'm sure. Yeah. Well, that's a disclaimer. Use the coil method that you mentioned. John PA1ZJN over on BAT Sisses. Thanks very much for this excellent presentation, Steve. It went far above my current knowledge, so a lot of new ideas to explore. I also want to thank the RSGB for keeping the option to chat without logging into YouTube, because many of you watch on YouTube, but we do also stream to the British Amateur Television Club, who give us a lovely streaming service as an alternative if you don't use YouTube. Marco PD50 says, would there still be a difference in modelling patterns when considering infinitesimal dipoles in horizontal versus vertical positions?
Well, the answer is whether the answer depends upon whether the dipole is in free space or over ground. The question makes no sense if you don't introduce ground. So let's assume that ground is present, and then in that case, the answer is yes. The patterns will depend upon the orientation of the infinitesimal dipole over the ground. If the antenna is in free space, horizontal and vertical have no meaning. The pattern will always be relative to the antenna, but it doesn't change if you rotate the antenna. So I hope that answers the question.
Okay, thank you, Steve. I hope that helped, Marco. Steve, you talk a number of times about small dipoles. Many people, particularly here in the UK, have quite small gardens or lots, as you say in the US, with a length of 50 feet or smaller. Do you have any advice on the best approach to build a dipole for 80 metres or even 160 metres in such limited circumstances? That from Stuart.
My suggestion is vertical monopoles. Vertical monopoles introduce the question of how to handle the radials. And I think it's a lot easier to come up with creative solutions for radials for a vertical rather than try to put up a full-length dipole horizontally. So, of course, the polarization is different. So that's the question is, if you're working DX, you want low radiation angle. you want your takeoff angle to be low. And I think that's easier to achieve with a vertical than with a horizontally disposed dipole, or half of a vertical dipole, which is the monopole over the ground screen. Vertical dipole, of course, if you can construct a vertical dipole, the horizontal area is small. I guess you may need some guy wires for a tower, so the guy wires will require horizontal real estate, but the antenna itself is just a vertical. Vertical dipoles have worked very fine. They're a very good antenna, and vertical monopoles over radials are a good antenna. And vertical monopoles over a, you can take the radials and replace them by a counterpoise, and the counterpoise can be curled up, and that works quite well. And Tom Schiller, N6VT, actually has a design. His website, I think, is called Next Generation Antennas. If you go to nextgenerationantennas.com and look up Tom Schiller's Bravo 8 antenna, it shows that you don't really need radials. You can construct a ring structure at the base of the antenna that's physically small, that will give you a very nice low radiation angle off your antenna, which is good for DX without a large horizontal footprint. So that might be something to consider. And of course, other folks, we've done balloon lofted antennas too, where you'll send up a weather balloon and pull up a wire, a vertical wire, and we've done that at field day many times. 160-meter vertical is suspended by a balloon, and work all over the world with that. So that's possible, but of course helium is expensive, and those balloons can't be used all the time. They sometimes they're not allowed due to airport or air travel regulations. But anyway, balloon lofted antennas are another possibility.
All right, thank you. That would finish the questions from our audience now. I've got one question I'd like to ask you. I always ask it of people who are expert at antennas. And that is, do you think there are significant new types of antennas and designs still yet to be discovered or invented?
The answer is definitely yes. Antenna engineering is going through multiple phases that I've noticed. One phase I've already mentioned was the transition to numerical methods that started around 1960. And from 1960 up until around 2000, maybe 2010, we reached a very high state of perfection. So the numerical phase was an era. Now we have all those tools available. After that came the era of materials. People started investigating making antennas out of new materials. Not just interesting shapes, although that was one thing. There was an era of what I'll call genetically evolved antennas, where just you use a metal antenna, but you make it a funny shape that's devised by a genetic optimization algorithm. They're called evolved antennas or genetic antennas. They sort of look like a paper clip that's been unfolded in a funny wiggle, and they can be designed to have good gain or good pattern or whatever you want. So there was that era of the genetically optimized antennas. Then the current era, well, before the current era, the next era after that, I'll say the materials era. This is the era of artificially engineered materials, photonic band gap materials, double negative materials, single negative materials, surfaces, metamaterial surfaces. So we discovered you can put materials under your antenna that work better than ground and even better than a mirror. These photonic band gap materials can be designed to give you, they pull your pattern all the way down, is just perfect, you know. Questions of how to do this to the amateurs. I just gave a a hint of that when I showed that antenna with the balloon radome. But you can certainly build things on the ground. Instead of radials, you can put your antennas over sheets made of stuff that's sort of like an artificial structure that will improve performance a lot more than radials will. And of course, all the work in metamaterials, single negative, double negative, negative refracting, photonic band gap, all of this whole area was the next phase or era. Now we're beyond that. We're in another era. The era is people are trying to overcome the two bounds. One is the Fano bound on impedance matching, and the other is the Chu bound on antenna bandwidth. The Fano bound, I've already showed one way around it is with these non-Foster matching techniques. You can get around the Fano bound. But the Chu bound is another animal. People are trying to figure out other ways of getting around it, so you can build electrically small antennas that still have good radiation properties. And the latest thing is what is called direct antenna modulation, where the antenna is either an array or a single antenna, but it's modulated in a particular way. And we're not treating these antennas using traditional antenna theory in the frequency domain. We're analyzing this as a time domain transient behavior. And the idea is to get high information capacity or bandwidth, high information capacity out of the antenna. And so we're sort of combining the modulation and the antenna together in a certain way. And so that's another thing. Let's see, I skipped one. Impulse antennas, ultra wideband. That was actually much older. That preceded the materials era. That was the idea that you can send impulses into antennas. That was sort of a groundbreaking idea. The work came out of Huntsville, Alabama, and also the USC Antenna Lab. That found its application in radar, and particularly penetrating radar through the ground, through the wall radar and ground penetrating radar. Through the wall radar was interesting because you can walk up to a wall and see what's on the other side of it with those kinds of radars. Look through the walls. So the antennas are popping up everywhere. The biggest push driver on antenna technology right now is wireless devices, making very tiny antennas in your wireless device. Your smartphone has got many, many antennas in it. It'll have GPS antenna, not just GPS, but GNSS. GNSS means your phone may very well receive not only GPS, but also the Chinese Baidu system, the European Galileo system, the Russian GLONASS system. You may have multiple geolocating capabilities in your phone, all of which operate on similar bandwidths, but slightly differently. And all of that on top of your Wi-Fi, your Bluetooth, and your primary cellular frequencies, or LTE frequencies nowadays. So your antenna design in your phone, your antenna actually is the limiting item in the size of the phone. They can make the phones even smaller, but they can't make the antennas much smaller without sacrificing performance.
No, I think we are all guilty, or at least lots of us are taking for granted what our mobile phones have in them now. But yeah. Anyway, it's really encouraging to hear from you that there are new antenna designs and techniques yet to be discovered. So we look forward to those. But for tonight, we want to thank you very much again, Steve Stearns, for a wonderful talk. And I'm sure you've inspired many to read more about it. Thank you very much, Steve.
My pleasure.
Thank you.
Good night.
Good night. And that does conclude this webinar. And our thanks once again to Steve Stearns, K6OIK. Also, thanks to the team who work on this webinar series behind the scenes. We hope you've enjoyed this Tonight at 8 and that you'll be able to join us next time when we'll be looking at the RSGB's online HF propagation tools with Steve Nichols, K6OIK. Well, these cold winter nights in the shack can be an ideal opportunity to make stuff. And this year's RSGB construction competition is now underway. There are lots of categories and incentives for new and young licensees, and the prize money has also increased this year. To support the RSGB strategic growth priority, there's also a new category called Reimagination. So if you think your project could be interesting to the maker community, or you have an idea which could encourage people from groups such as men's sheds to try amateur radio, then this is the ideal category for you. For more information on the competition, please visit rsgb.org/construction-competition. The construction competition deadline is March the 1st. If you'd like to see details of future webinars or watch recordings of previous programs in this series, please visit rsgb.org/webinars, where you can also send us comments and feedback. And if you subscribe to the RSGB's YouTube channel, you'll be notified of all upcoming Tonight at 8 webinars, as well as other new videos and presentations from the Society on a wide range of amateur radio topics. Thanks again for joining us this evening, and until next time, this is David G7ERP signing off and clear. Bye-bye.